Hey there. So today we're going to continue talking about the hydrogen atom, and we're going to discuss the Zeeman effect, which we introduced in the very first lecture as a problem with the Bohr model of the atom. So today all will be explained. All right, but first a little bit of a recap. In the previous two lectures, we discussed the fact that when you solve the Schrödinger equation for the hydrogen atom potential, you get three quantum numbers to cover the three spatial directions. And those three quantum numbers are n, l, and m sub l. They all stand for different things. N is the principal quantum number or the energy level. It can start at 1 and go up from there. And the energy of that level is, for the hydrogen atom, minus 13.6 eV divided by n squared. So once you know n, you know what the energy of that electron is. The orbital quantum number is L, and L is fixed in its values, its possible values, once you've chosen your energy level. So L runs up to, from 0 up to n minus 1. L gives you the magnitude of the angular momentum of the electron in its orbit around the proton, okay? So the value there is L is equal to h bar times the square root of little l times L plus 1. Okay, so those are what our two previously covered quantum numbers were. Today, I want to introduce the third one and give you its physical meaning. So remember that m sub l is called the magnetic quantum number, and its values run from minus L to plus L in integer steps. So the values of m sub L are fixed once you've chosen your value of L. Now it turns out that what the magnetic quantum number actually means is it gives the z component of that angular momentum. The z component of the angular momentum is equal to h bar times the magnetic quantum number value m sub L. What this means is that the direction of L is somewhat fixed by the magnetic quantum number. This idea is called space quantization. For that, let me give you this little cartoon to help you understand. If you know the magnitude of your vector, the length of it, which we do once we've solved for L, h bar times the square root of L times L plus 1, and you know the z component, then what that does is it sets certain values of an angle in between the z-axis and the vector L. All right, so that's shown here. This is for L equal to 2, little l equal to 2, and then that means that m sub L can run from minus 2 to plus 2 in integer steps, which fixes the z component, but the length is also fixed. And so you can see here there's a definite set of 5 possible values for the orientation of your angular momentum, and that's shown here. Okay, the length is root 6 h bar, and the z component can run from 2 h bar all the way down to minus 2 h bar in integer steps of h bar. All right, so this is the idea of space quantization. Now, of course, if you know the z component and you know the length, then you can also figure out what the angle is between the z-axis and your vector. Okay, so that's given by the cosine of theta is equal to Lz over L. The h bars cancel on the top and the bottom, and so you have ml over the square root of L times L plus 1 is equal to cosine of theta. And so then you can solve for what theta is. So for example, what would be theta for a state with the quantum numbers n equal to 2, L equal 1, and ml equal to minus 1? Well, we can solve for that, right? For L equal to 2, for L equal to 1, then we have the magnitude of our angular momentum is root 2 times h bar. And if ml is equal to 1, then that means that Lz, which is equal to ml h bar, is equal to h bar. So then cosine of theta would be Lz over L. So that would be h bar over h bar times the square root of 2, which simplifies to 1 over the square root of 2. And then if you do the inverse cosine, you can find the angle, and that angle is 45 degrees. So for that particular state, the angle in between the z-axis and your angular momentum would be 45 degrees. Well, you might be asking yourself, why z? I mean, what's so special about z, right? Why not x or y? Heck, why not all of them? Well, z is somewhat arbitrary. We really could pick x or y, and then it would just be the restriction on lx or ly. But the thing is, we can't pick all three. Heck, we can't even pick 2. We can really only know one component of our angular momentum vector, and we can know the total length, but we can't know 2 components, because if we knew 2 components, then we'd really know 3 components. And if we really knew 3 components, what that would mean is that we violated our uncertainty principle. Remember the Heisenberg uncertainty principle from Modern 1? The Heisenberg uncertainty principle says that you've got an uncertainty in your position and you've got an uncertainty in your momentum, and the limiting values of the product of those two things is going to be h bar over the square root of 2, or I'm sorry, h bar over 2. So that means that you can't precisely know exactly your position and your momentum, right? At the same time, you can't know them. Remember, the angular momentum, though, is the cross product of the position and the momentum. So what that means is that if you know all three components of your angular momentum, you really are violating the Heisenberg uncertainty principle, and you can't do that, okay? Now, we can say something about what the average is. We would sort of expect that in the absence of magnetic fields or anything else, that the angular momentum components, the average of the square of the angular momentum components in the various directions would be the same, okay? Because Lx squared plus Ly squared plus Lz squared should equal to L squared. That's just vectors, right? Okay. So if we can say that, then we can say that the total value of our angular momentum squared is equal to 3 times the average value of your z component squared, okay, if we're talking in averages. Now, remember that for this, the Lz would be the mLh bar. There's different possible values of m sub L. It runs from minus L to L in integer steps. So if you want to sum over all those and figure out your average, then you can do that. That's shown in this handy little equation here. The 3 just comes from the fact that there's 3 components and we expect the averages of the squares to be roughly the same for all 3. So instead of saying, you know, Lx squared plus Ly squared plus Lz squared, we said 3Lz squared, okay? Okay, so now this is the average value. To get an average value, what you do is you sum up your values and you divide it by the total number of values, right? Well, that 2L plus 1, remember that's the total number of possible values of m sub L. Okay, so if you go minus L plus 1, and so on and so forth, all the way up to L, then you've got 2L plus 1 values of m sub L. You can check it out. It works out well. So for example, if L is equal to 1, m sub L could be equal to minus 1, 0, or 1, and then that's 3 possible values. Well, 2 times L plus 1 is 3. So there you go for L equal to 1. All right, so that's just like saying, here we're dividing by the total number of possible values from ML. We're summing over all possible values of LZ. Okay, so that's what we get. Now you can show that this little inequality is true, or this little summation is true, and I've chosen L equal to 2 to give you an example of that. So if L equals to 2, then ML is 2, 1, 0, minus 1, and minus 2. And so I've done the sum for all the possible m sub L values there. And then I have 3 over 2L plus 1. That gives me 3 over 2 times 2 plus 1. And then I'll multiply everything by h bar squared. When I do that and simplify it, I get 3/5 times 10 times h bar squared. And then that gives me 6h bar squared. Now, looking at the right-hand side of the equation, if I say L times L plus 1 h bar squared, I get 2 times 3 times h bar squared, which is 6h bar squared. So you can see that this little simple equation here describes reality very well. Okay, but uncertainty principle says we can only know one component, and we've picked Z sort of arbitrarily as the component that we want to describe. And really, we could orient our coordinate system in any direction we want, right? We could point Z this way or that way or that way. So really, just picking one and sticking with it is fine. And all textbooks generally do pick the Z-axis, so you're good to go there. Okay, now why does all this matter anyway? What's the big deal? Well, it turns out that really the key here is that there's a degeneracy in the energy states for the electron and the hydrogen atom. Now, you might need a reminder from Modern 1 of what degeneracy says. Degeneracy means here. I'm not talking about Marilyn Manson and Mickey Ears Degenerate, okay, which is on the March 2015 cover of this magazine called Paper. Not that kind of degeneracy. I'm talking about an energy level thing from quantum mechanics, all right? We introduced this in Modern 1, and the definition of degeneracy is if you have different sets of quantum numbers that give the same energy, then that's called a degenerate state, okay? This came up when we were talking about the infinite box, the infinite square box, okay? And there were different sets of quantum numbers that gave the same energy, and we introduced that idea last semester. Now, the same thing is happening in the hydrogen atom. We have degeneracy in the hydrogen atom. Because the energy is dependent only upon the value of n for this particular case, okay? So remember, E sub n is equal to minus 13.6 eV divided by n squared. L and ml don't appear in that equation, which means that the values of L and ml don't change the energy level, all right? Okay, so if the values of L and ml don't change the energy level, and there's more than one possible value of L and ml, then you have yourself a degenerate system. So for example, if you're in the 2p state, which to remind you means the p means L equal to 1, then you've got 4 possible combinations if you ignore spin, okay, which we haven't even talked about yet, so we're good to go there. But you've got 4 possible combinations that result in the same energy level. You've got L equal to 0, ml equal to 0. You've got L equal to 1, ml equal to 1. You've got L equal to 0, ml equal to 0. You've got L equal to 1, ml equal to minus 1. All right, so those are your 4 possible values, and they all give you the same energy. So that's a degenerate state. Now, you might be thinking, okay, I'm still not seeing why this is important. All right, so there's degeneracy, and so there's the z component of angular momentum. Why do we care? Well, it turns out that in certain conditions, like in the presence of a magnetic field, especially a strong magnetic field, that you can lift that degeneracy. The degeneracy is broken, and the different values of ml will actually split into different energy levels, and you can see this in the spectra of atoms. All right, so that's kind of cool, and we're going to describe why. Well, in order to describe why, we need to review some introductory physics. I'm not sure if you remember this, but in Physics 1151, you were introduced to the concept of a magnetic dipole moment. All right. Now, this comes about because currents create magnetic fields. Geez, I hope you remember that. So if you have charged particles moving in a path, right, then that creates a magnetic field. Well, what's an electron moving in an orbit, okay, about a nucleus, if it's not basically a little current loop? All right, so you're starting to see now. You're starting to get the picture. So currents create magnetic fields. If you have, say, a circular current loop, at the center of the current loop, we define the magnetic moment, which points in the direction that the magnetic field points at the center of the loop. You can figure out what direction this is by using the right-hand rule. You take your right hand, you curl your fingers in the direction that the current is flowing, and then the magnetic dipole moment, or the magnetic field at the center of the loop, will point in the direction of your thumb. Okay, so that's here. Now, the value of the magnetic dipole moment is defined as the current flowing through the loop times the area vector. Okay, and the area vector is just the area of the loop, the area enclosed by the current loop, and then the direction is picked by that right-hand rule that I talked about just a minute ago. So IA is the magnetic dipole moment, mu, of the loop. The units of this, of course, are amps meters squared. But what's important about the magnetic dipole moment is that in the presence of an external magnetic field, in other words, not one generated by the loop, but another one, maybe a bigger one, what'll happen is it acts like a little bar magnet, and in the presence of an external magnetic field, your magnetic dipole moment will rotate to be aligned with that external magnetic field. Okay, it causes a torque, in other words, on the current loop. The magnitude of the torque is equal to the cross product between your magnetic dipole moment and the magnetic field. All right, so this is all basic physics 1151. If you need a refresher course, you can Google it or go to hyperphysics or something like that and catch up. Okay, but this was all covered in physics 1151. So we've got our magnetic dipole moment. In the presence of an external magnetic field, it rotates. Because there's some rotation going on, it's causing some energy changes. That means that there's also a potential energy associated with this value. The equation for the potential energy of a current loop in the presence of an external magnetic field is equal to the dot product, the negative dot product, between the magnetic dipole moment and the magnetic field. So U, in other words, is minus mu dot B. Now, the energy of the system is minimized when the magnetic dipole moment is aligned with the field, because then you would have mu B and then cosine of 0, right, times minus 1, so that's minus mu B, all right? And then it's maximized, the energy is maximized When they're anti-parallel, when they're pointing in opposite directions, that's a very high energy state for the system, and it goes up to plus mu b. So that kind of explains why, if you like a why, the current loop likes to rotate, because it wants to minimize that energy, that potential energy of the system. Okay, so remember I told you that if you have even a single moving charge, that you can sort of consider that to be a low current loop. All right, so now let's go back to our hydrogen atom. We're going to kind of go semi-classical with this just so you can conceptually understand what's going on. Bear in mind, I'm sort of using the Bohr model here. It works pretty well, so that's nice in this circumstances. Sometimes the Bohr model works, sometimes it doesn't. This actually gives a correct prediction, so we're going to go with it for a second. But bear in mind, this isn't quite the real story. Okay. So we have our proton, we have our electron orbiting around it. Okay, let's assume that it's a circular orbit. This is very Bohr model. All right. So my magnetic dipole moment for the Bohr model would be the current times the area enclosed by the loop. Now current is just a charge per unit time, Q over T times A here. Okay, my charge is E, or actually minus E. E is being 1.602 times 10 to the minus 19 coulombs, which is the charge on an electron. Okay. Now the time would be the period, which is the circumference of your circle, which would be 2 pi r, divided by your speed, which is v. Okay, that's the speed of your electron in your orbit. And then A is the area enclosed by the loop. If you assume a circle, that's pi r squared. So that leads us to our equation minus E pi r squared over 2 pi r over v for our magnetic dipole moment. Now we can simplify things a bit. Some of our r's cancel, our pi's cancel, and then we end up with an equation minus ERV over 2. All right? Well, remember that the angular momentum is defined as r cross p, which for a circular orbit is just going to be r times mv, or mvr. Okay? So if we multiply the top and bottom by m, in other words, multiply by 1, then we have mvr on the top, which is our angular momentum. So we sub in for that, and it's minus EL, and then we end up with 2m on the bottom. So that gives us our magnetic dipole moment for the Bohr electron, all right, minus EL over 2m. If you put it in vector symbols, vector terms, then you have the same thing with vector symbols over the top, all right. So that's basically saying that if you have a charged particle that is moving in an orbit, right, it's moving in an orbit that gives it angular momentum, and then the angular momentum of the charged particle, the combination of having a charge and moving in an orbit, gives it a magnetic moment. Okay, in other words, it's creating a little current loop, so it's generating a magnetic field, and you have yourself a magnetic dipole moment for your electron in the orbit. Now, if you want to take the z component of both those sides, then you just end up with Lz, and you end up with mu z on the left-hand side. Okay? And remember that Lz, we defined that as ml times h bar, so you can plug in for that. So that means that the z component of our magnetic dipole moment is minus E m sub L h bar over 2m. All right, so there we have it. Now, the m sub L will pull out. Let's look just a second at this constant E h bar over 2m. Here, m is the mass of our electron, okay? And this constant pops up so much that they've actually given it a name. It's called the Bohr magneton. And the value of EH bar over 2m is 9.27 times 10 to the minus 24 amps meters squared. So when you put it in SI units, that's your value. And because it gets used so much, we have even given it its own little symbol, a mu with a little b subscript, so mu sub b. And that's our Bohr magneton. All right? Another point that I'd like to make here is that because the charge on the electron is negative, it is important to realize that your angular momentum and your magnetic dipole moment vectors point in opposite directions, okay, as is shown here. Now, one thing that the Bohr model doesn't quite get right, okay, is that your angular momentum vector isn't going to point straight up through the orbit like it would in a classical system. Because the magnetic moment of the atom can be related to the angular momentum vector L, the discrete direction of L also translates into the fact that mu is quantized. All right. So, in other words, the values of L are going to point along those angles, and then the values of mu sub n would just point in the opposite directions, like so. Okay. So you get the same kind of deal. So that's what the Bohr model gets wrong. Okay. Okay, now you still might be saying, why Z? Okay, well, we just chose Z as the direction of an external magnetic field. So let's say that now we put our Bohr atom or our electron in its orbit into a magnetic field, an external magnetic field. Well, it's got a magnetic dipole moment. So what'll want to happen is it'll want to rotate the atom to align with that external field. All right, so it would like to line up. There's a torque on it. However, it can't quite line up, can it? Okay, if we pointed our angular momentum vector directly along our magnetic field, well, then we would know exactly what the components of our angular momentum were, and that would violate the Heisenberg uncertainty principle. So what happens instead is you have a magnetic field, and then it'll align as much as it can, right? But it'll still be in one of these restricted values according to what its ML value is. Now, what's going to happen is because the values of Lx and Ly cannot be fixed, you can't know those. So what's going to happen is your angular momentum vector will precess about the external magnetic field, okay? So it'll kind of loop around. Remember, if it just hung out there and pointed in one specific direction all the time, that would violate the uncertainty principle. It can't do that. So here's my magnetic field, here's my direction, and then it's going to go like this and precess all around, making a cone, okay, with the possible values of the vector. Okay, well, you still might be going, so what? Okay, why does this matter? It's stupid. Why are you talking about this? Well, here's why. This all explains, or helps to explain, one of the main difficulties with the Bohr model of the atom. And that main difficulty was the Bohr model couldn't successfully explain why spectral lines split, okay? And this was known as the Zeeman effect. In the presence of an external magnetic field, what was one spectral line would split into multiple spectral lines, oftentimes 3, okay? And this wasn't able to be explained with the Bohr model, right? But we can explain it now that we understand about the magnetic quantum number, all right? What happens is these different values of m sub L give different magnetic dipole moments. And in the presence of a magnetic field, okay, that U is equal to minus mu dot B kicks in, and then you have a splitting of your energy level dictated by that equation, U is equal to minus mu dot B. If your value of L is, for example, 1, then you have 3 possible values of your m sub L. It could be 1, 0, minus 1, and that gives different values for what that U value is. U is equal to minus mu dot B, all right? So there it splits into 3 possible levels in the presence of an external magnetic field, giving the splitting of the spectral lines. Let me show you what that looks like mathematically. Here's my equation for the potential energy, right? This is the potential energy shift in the presence of a magnetic field. So here we have U is equal to minus mu dot B. Well, the dot product is the projection of mu along B, which is, as we've discussed, the Z component. So here we have minus mu Z times B. Remember that my mu sub Z was related to my angular momentum by this equation E LZ over 2m. Okay, so that subs in, and then we multiply that times B. All right. Now, if you break that down even further, LZ is equal to MLH bar, so you can plug in for that. And then remember, EH bar over 2m is the Bohr magneton, so you can sub in for that. And you can see that the energy level will shift, U will shift by the value m sub L times the Bohr magneton times my magnetic field. All right? So when the magnetic field is applied, for example, in the 2p level of an atomic hydrogen, it's going to be split into 3 different energy states. All right? If ML is equal to 0, no harm, no foul, you've got no shift, okay, because U is 0. And that's just going to give you whatever the energy level was before. But if ML is equal to +1 or -1, then that shifts the value of your energy state by the amounts plus mu B times the magnetic field and minus mu B times the magnetic field, and that splits it into 3. In other words, the degeneracy is lifted in the presence of this magnetic field because of the magnetic dipole moment of the electron. All right? So, whew, that's why the magnetic quantum number is important. It resolves one of the main problems with the Bohr model of the atom. Okay, let me do an example problem for you. You have a hydrogen atom, and it's in an excited 5F state in a magnetic field of 3 Tesla. So how many energy states can the electron have in a 5F subshell? And then, what's the energy of the 5F state in the absence of a magnetic field, and what will be the energy of each state in the 3 Tesla magnetic field? All right, so remember that an F state, SPDF, 0, 1, 2, 3. Okay, so that means L equal to 3. And then M sub L can have the possible values of +3 all the way down to -3 in integer steps. All right. Now, since your potential energy is the Bohr magneton times ML times B, that means there's 7 possible energy states in the presence of a magnetic field. Okay. In the absence of a magnetic field, there's only going to be 1. Right? And that is given by minus 13.6 eV divided by n squared, and here n is equal to 5. So that's minus 13.6 eV divided by 25, which gives you minus 0.544 eV. So that's our energy. All right? Now, with the B field on, the energy is going to shift from that value of minus 0.544 eV. How will it shift? Well, the Bohr magneton is 9.27 times 10 to the minus 24 joules per Tesla. If you switch that over to eV, which is a more convenient unit for this problem, then the Bohr magneton becomes 5.79 times 10 to the minus 5 eV per Tesla. Right? Now, plugging that into our equation, mu B times ML times B, then we have, for example, for ML equal to 1, 5.79 times 10 to the minus 5 times 1 times 3 Tesla, and that gives us 1.74 times 10 to the minus 4 eV. All right, so what I've done is I've taken that number, and remember what's going to happen is for these various states, we're just going to take that number and multiply it by, minus 1, minus 2, minus 3, or 2 and 3, and plug into our chart. And then we have minus 0.544 plus these different values of integer constants times this 1.74 times 10 to the minus 4 eV. All right, and so that gives you the energy level breakdown. Now you can see that there's 7 different energy levels here, but they only differ by, 1/10,000th of an eV. So you can see why it took them a while to discover this problem with the Bohr model of an atom. You have to have a really good spectrometer in order to see this splitting. It's a very fine sort of splitting, but once you get a spectrometer that's good enough, you can see it. All right, and it's there, it's obvious. Okay, so, whew, that was a big one. The Zeeman effect kind of explained what's going on. To recap, you have an electron in an orbit. Because that electron is making a little current loop, it creates its own little magnetic field. The magnetic field at the center of that loop, where the proton is the magnetic dipole moment. In the presence of an external magnetic field, that magnetic dipole moment wants to align and rotate with it with respect to that magnetic field. It wants to line up. Because, however, of the uncertainty principle, it can't. If it did line up exactly with that external magnetic field, that would violate the uncertainty principle. We would know the position and momentum components. All right? So it's stuck in these various different orientations with a certain angle with respect to that magnetic field. Because these are discretized, because of space quantization, all right, what that gives is different values or projections of that magnetic moment. And in the presence of an external magnetic field, that lifts the degeneracy that is present in that energy state. So that's what the magnetic quantum number is, and that's what it does. All right. I hope you got all that, but if you didn't, you can always rewind and watch it again. Email me with any questions. Thanks.